Most of the topics for this week involve linked lists in some way. And although generally it's been the case that I haven't been using these videos to talk about data structures at a high level because they don't quite fit with the format of the videos, there is one data structure, one that you've seen before in various cases, that I would like to talk about to begin with, just to put our minds in the right place, because we're going to spend a lot of time with linked lists this week, but we often use linked lists to implement certain other data structures as one of behind some abstraction. So in this case, the abstraction is that of a stack. So a stack is a very simple abstract data type. So behind this IntStack class, there could be a variety of different mechanisms. We could use vectors or lists or anything else. We're going to use a raw linked list for it today. But the stack exposes two key operations, and they are traditionally called push and pop. And the idea of the stack is much like an actual stack of things. So we start stacking things up from the bottom upwards. The push operation places something on top of the stack. So if I perform these three push operations in order, we push 10, then we push 6, then we push 17. The pop operation removes the thing on the top of the stack. And the idea behind a stack is just like a stack in real life. You can only really interact with the top of the stack. If you want something that's in the middle of the stack, you have to first pick up everything above that thing. So here I'll do the pop to remove 17, and then I'll push the value 187. And it's very common for a stack type in a programming language to deliberately restrict how you can interact with it. So in this IntStack object allows you pretty much to push things onto the top, remove the thing that's on the top, and ask the simple question, is the stack empty or not? That's it. If you want something that's halfway down the stack, you have to remove a bunch of elements to get there. You are not allowed to see into the stack beyond the top element. Now, it's a question for another time why I might want to arbitrarily restrict myself like this. So why am I writing a data structure that even though underneath it might use a list or a vector, and we know those allow us to go halfway through the data structure, why is this class not giving me that option? And one of the reasons is because of the abstraction. If all I need is push and pop, it's nice that the class doesn't provide more than that, because then it's not making any extra promises than it has to. And so in this case, what I want to do is write the IntStack class and these three operations, push, pop, and isEmpty, using a raw singly linked list as the backing storage. So we've talked about linked lists before, and we've even talked about them in videos. Technically speaking, linked lists are review in this course. So if you want to talk about linked lists from the very beginning, you may want to go back and take a look at some of the CSC 111 videos about linked lists. We talked about linked lists in a video about halfway through the course when we talked about the overview of the standard collections. You can also take a look at that, and I'm sure it's come up in lectures since then. But the idea here is that what I will do, normally I draw linked lists with this notation. I use boxes, but it's not a box like I might use on a scoping diagram. Instead, each box represents one node of my list. So here I have a linked list with 3 elements. So there are 3 nodes. Each node contains 2 pieces of information, an element, in this case an int, and directions to the next node. And the very last node, as its directions to the next thing, contains a null pointer as a way of signaling there is nothing left in the list. To keep track of where the list begins, we have this one special pointer that's conventionally called head that tells us where the first node is. My goal for today is to implement my stack using a singly linked list with the idea that the bottom of the stack is the end of the list and the top of the stack is the beginning. So to push something onto the stack, what I'm really doing is splicing a node between the head pointer at the beginning of the list after the head pointer. I guess you couldn't say after the head pointer. The node becomes the new head of the list, and the previous first node is the node after the node I just pushed. And hopefully you can see that and I guess verify to yourself that it doesn't matter how long the list is. Pushing an element onto the top of the stack will therefore take very little time because it requires just one local modification. One of those things we already know is a benefit of working with linked lists. So my goal for today is to implement that. And the reason we're doing this is mostly to phase back into working with linked lists directly. I think it also provides an excuse to review some things from last week, like the use of shared pointers, the ability to define types inside of classes, and then finally, as we'll see in the next video, we're going to make our stack type parameterized so I can make stacks of anything, not just ints. So here is our IntStack class. We've got a constructor, and the prompt is saying specifically, although the stack class presents an abstraction, and therefore we could use all sorts of things to implement the stack underneath, including a vector or an STD list, the prompt is insisting that we use a singly linked list ourselves. We make our very own list to set us up for the next few videos this week. So I have a constructor. I've got a push function, which takes a value v and puts on the top of the stack. I've got this function isEmpty, which tells us if the stack is empty or not. Because the stack currently has nothing in it, we just say true always. I have a pop function, and this pop function doesn't just delete the element on the top of the stack. It also returns the element that was removed. And of course, we can't pop from a stack that is empty. So before I implement any of those, I am going to need some machinery to actually represent the nodes of my list. And because the node itself consists of two pieces of information, I guess it's clear I'm going to need either a structure or a class to represent a node. I'm going to have the structure or class that I write live in the private section of int stack, because it shouldn't be anybody's business in the outside world how I'm storing the stack. They just call push and pop. Because I think that the node I'm going to write is pretty basic, it's pretty much just data. Maybe I'll add a constructor or some other behavior, but it's pretty much just data. I'm going to use a struct for it. I'm going to call it struct node. Now this type lives in the private section of the instack class, so nobody outside the class will ever be able to even see it. But just in case we care, the full name of this type, so inside of the instack class, I can just say node to refer to this. But the full name of this type is instack : node, because it's a structure called node that lives inside the instack class. Okay, so actually we'll put that comment, we'll just put that up here. Okay, so inside my node, what do I want? Well, let's see. I guess what I want is an element, so we'll call that int element. Okay, great. And then I want a pointer to the next node in the list. Okay, so how am I going to represent my pointers? Well, it should be clear that I would really like to avoid using raw pointers if I possibly can, because we know that that requires the use of the new and delete operator. We know that our list, the nodes of our list, need to continue existing, for example, after the push function has ended. I'm going to use the push function to add stuff to my list, but of course I want the node to continue to exist when the push function is over. That should already be a hint that we're going to need dynamic allocation. I'm going to need the node to be allocated outside of any particular scope. I really don't want to use the new and delete operators. And it turns out that this is a very valid use of shared pointers. And I can sketch out why shared pointers are an appropriate thing to use here. So I've got a bunch of nodes of the list, and each of the pointers between nodes will be a shared pointer. And then at some point in the future, I decide to destroy the list. Well, how about this? I'll just lose the head pointer. So suppose that the instack class gets destroyed and the head pointer is lost. Well, wait, the head pointer is the last thing that points to this node, and therefore the node object has to get destroyed. As part of destroying the node object, we lose this pointer, which if it's a shared pointer would understand it might be the last pointer to the next node, which destroys the next node. And then we lose this pointer, and it destroys the node after that. Oh, whoops, I pasted by accident. And so we can see that if I have my singly linked list represented by a chain of nodes with shared pointers in them, the entire list will get destroyed for me as soon as I lose the head pointer. And in general, as soon as I lose the last pointer to a node, the shared pointer can take care of destroying the node for me. That is not true of all data structures. There are some data structures where shared pointers don't quite work, and we'll talk about that some other time. But for a singly linked list, they do. So I want something like this: shared pointer to type node next. All right. But then I realize, I'm going to need a lot of these. I'm going to probably be throwing around a lot of shared pointers to nodes. This is a good time to check that I've included the memory header. Okay, I did. And so I'm going to throw around a lot of shared pointers to nodes, and I may not want to always write them out this way. So I'm going to do something similar to what I did last week, which is I'm going to define my very own type called node pointer. So I'll say using node pointer, to be equal this, the longer name of the type, then I'll just be able to say the node contains node PTR next. Now there's something weird that's going to happen here. I'll try compiling to show off an error that we've just created. And the compiler is unhappy, but if we trace it back, it says line 40. You're creating a type called node pointer, and node pointer is supposed to be a shared pointer of node. But I don't know what node is. And the compiler has a good point, because at this point in the code, on line 40, you have not yet defined a type called node. Okay, so why not just put that down here? And you might be having a flashback to a lecture about linked lists in C right now, where we had almost the same problem of when do we name this type? So I'll try that. And the compiler still doesn't like it. Now it says, sorry, line 42, what the hell is a node pointer? Okay, so I'm damned if I do and I'm damned if I don't. I mean, if I define node pointer up here, it complains about type node. If I define node pointer down here, it complains about type node pointer. So what do I do? Okay, how about this? We'll just put node pointer back up here. What I could do is declare my node type in advance. So give a forward declaration. Recall that if you want to warn the compiler that a particular type exists, you can declare the type up here with no further information. So I just say struct node. That's a way of telling the compiler, there is going to be a type called node, just give me a minute. And that allows the compiler to trust me when I say later, yes, node pointer is shared pointer of type node. Just leave it there, hold on, let me get everything else in order. So if I try that, we'll see if the compiler can put up with that. And it doesn't give an error. It obviously complains that the code is incomplete, but of course the code actually is incomplete. So you'll see this pattern a few times in the next few videos. We have to keep using this sort of strange struct node appearing twice. We have to use this so that we can declare a pointer type that I can then use inside the node type. There are a few other ways around it. I think all of them are a bit clunky. I think this is the cleanest one. Okay, so my node object is a pointer and an element. Now recall that a struct and a class are only different in one way, and that is that if you don't specify public or private, all of the members of a struct are public by default. So in particular, I can give this structure member functions or constructors or destructors. I don't really need most of those things because the node is mostly just a bucket of data. One thing that I think might help is adding a constructor here. So because I often want to construct nodes, giving both a pointer and an element, I might want to write a constructor that handles those things. Keeping in mind, I could actually just construct the node the usual way I construct structure types with no constructors, so just giving the data members. But writing a constructor myself might be an easier way of allowing me to modify that later, for one thing, but also making it more readable that that's what I intend to do in my code. So I'll say int, I guess I'll take the members in the same order. Node PTR, we'll call it NXT instead of next, and then int the element. Okay, and all that's going to do is initialize the pointer and the element for now to be the values that were provided. So I initialize my next pointer to be NXT. I initialize my element to be the element. And the constructor otherwise does nothing. Now, to be clear, if I delete this, it turns out the code I'm about to write will still work because the default construction system the compiler uses will be able to allow me to initialize these values directly. I think having a constructor is still helpful here. It makes it more clear that I'm intending to use it, and it means later if I want to add any more functionality, I can do so. All right, so I now have a type to represent my node. What I need to do now is begin chaining together the elements of my list. I need one more thing before this int stack object can store a list. I need a head pointer, a way of indicating where the beginning, where the first element of my list, the top of my stack is. So I will add a class member to instack called head. All right. And so now, inside of my class, I use my head pointer to iterate over my list if I need to, or to access elements of my list. For this video, I'm actually not going to need to iterate over my list at all, because all I'm doing is working with the top of the stack, which is the first element of my list. Maybe it'll be helpful if I just draw the list in, or I draw something in for us to work with here. Okay, so here's a list that has, let's restore our list with 3 nodes. So there's 6, there's 10, and then there's 17. And then the 17 points to nothing. And we could also have a list. What we're working with typically when the class is created is an empty list, which would be a list where the head pointer points to null. That's a way of indicating there is no first node, which means there are no nodes at all. I suppose I should start by implementing that. So if you create an int stack object, we're not going to bother with the initializer list constructor right now. If you can create an int stack object, I will initialize the head pointer to be null. So the head pointer points to nothing, the stack is empty. And right off the bat, I guess I can implement my isEmpty function. So I'm going to return whether or not the head pointer is null. If the head pointer is null, then the stack is empty. Otherwise, it isn't. I suppose I could also write that with an if statement to make it more clear what I mean by that. Okay, if head equals a null pointer, then the stack is empty. Otherwise, the stack is non-empty because there must be at least one node if head points to something. All right, now it turns out that any other time I want to check if the stack is empty, I could just call the isEmpty function. So that's the last time I have to worry too much about the head pointer equaling null. I guess I'll erase my empty list from this over here, just so I can add some more space for the next thing I'm going to do. Okay, so now I want to push an element onto my stack. I want to create a new node, and then I want to splice the node in right before the first node of the list as it currently stands. So first I'll create a new node. There is a way of, I think, doing this as a one-liner, but I'm going to do it with a couple of lines to try and unpack it a little bit. So I'm going to say node ptr new node equals, well, I'm going to call make shared because these are shared pointers. Make shared, I'm creating a node object, and now I give the constructor arguments. So what goes in the round brackets for make shared are the constructor arguments for the thing I'm creating. That's one of the reasons why I added an explicit constructor here, is to make it more obvious what I'm actually doing. And if you wanted to, you could take a look at the posted code and actually add a print statement in the constructor to verify that it is indeed being called when I do this. Okay, so the constructor arguments to a node object are the thing that comes after that node and the element to insert. Okay, so what comes after the new node I'm making? Well, how is that going to work? Well, I'll go over to my diagram. Suppose I want to push the value 187. I want to make a node whose element is the value you gave me, so v, and whose next pointer points to what is currently the beginning of the list. So I guess I can get the beginning of the list by looking at my head pointer. And so I use head comma v. So this is what it points to next, the current beginning of the list, and then the value you provided me. Okay, and then what I want to do is I want to redirect my head pointer to point at the node I just created. So I want to do something like that. So head equals new node. Maybe you can see that there was a one-liner alternative here where I don't even bother giving the new node a name, but it can help. And as I said in 111, as I'm sure many of you still remember, when you are working with linked lists, keep a diagram over on the side and do a sort of mock-up of your operation one step at a time. That's one benefit to expanding it out to be multiple steps, is it's easier to make sure you don't skip over something. I think, though, that I now have my push operation taken care of. If it looks unnaturally short, so for those of you that weren't thinking about the one-liner, but instead thought this should be 3 or 4 lines, one of the reasons it might seem a bit short is that this call here is doing a bit more work than might seem obvious, because it's calling the constructor for the node object, which is setting those two things for us. That's why this function seems a little bit on the short side. Okay, next, what about the pop function? So the pop function's job is to go grab the very first node of the list, remove it from the list, and then return the element stored in the node. So a key thing to observe here is, normally to delete the first element of the list, all you have to do is redirect the head pointer to point at the next element of the list, and then delete the node that was there. In our case, we don't need to delete it because these shared pointers will take care of that for us. We do, however, need to save a pointer to the node, because if we don't save a pointer to the node and we redirect the head pointer, how are we going to return that element? Okay, so what I'll do is I'm going to deliberately use more steps than I need again. I'm going to call this node to delete. Well, that equals the current beginning of the list, the current head pointer. On line 39, I can assume that the head pointer points to something, because on line 37, I checked that the list was non-empty. So if the list was empty, an exception got thrown. All right, so my node to delete, I guess I've got this pointer node to delete. Now what I want to do is reconstruct the list. I want the list to now have this node excluded. So I'll say, okay, well, my head pointer is now going to be whatever comes after the node that I was going to delete. Okay, so head pointer is node to delete arrow next. And recall that because what I'm the target of the pointer here, so node pointer is a pointer to a node. If I want to actually work with that node, I have to use the arrow operator. Okay, so head equals node to delete arrow next, and that sets us up for the situation we already have in our diagram. Currently, as of this line, the thing I was going to delete is now out of my list. All I have to do now is return the element that was stored inside of it. So I return node to delete arrow element. And what will then happen is there is only now one pointer to the node, and it's the pointer called node to delete, which is a local variable of my pop function. When the pop function ends, this node pointer object, node to delete, will be destroyed. And because it's a smart pointer, in the destructor for the shared pointer, it will observe that it is the last pointer to this node, and that will trigger the destruction of the node. And if you don't believe me, you could add a destructor with a print statement in it to the node type to verify that yes, indeed, the node is being destroyed when the pop function ends. And it's great that we don't have to worry about calling the delete operator here, that smart pointers have our back. All right, I think I've made a good first try at my push and pop functions. We'll see if the compiler wants to complain. Looks like everything's fine. Now let's try running it and see what we end up with. So I should push the elements. We'll just mock up what I expect to see here. My stack should contain, we'll just sketch it out. I push 10, then I push 6, then I push 17. Then I should print out, I'll just write the output that I expect here, part 1, and I pop the stack. So I should print out 17. Then, so 17 is now gone. I push 187, and then I pop every element of the stack until it reports that it's empty. So I should see pop 187, pop 6, and then pop 10. All right, we'll try running it and see what we get. All right, and sure enough, I print out 17, and then I pop 187, then 6, and then 10. So I like this class because I think it's a nice basic use of linked lists. I'm not iterating over them. All I'm doing is adding stuff to the beginning of the list and removing stuff from the beginning of the list. And it's sufficient to be able to implement this very simple data structure of a stack. And we can see we have these push and pop operations. And of course, in main, because of abstraction, we actually have no idea what the stack is doing, nor do we care. All we know is it provides those key operations of the stack, push and pop, and the convenience of asking if the stack is empty. So we're not quite done with this. I would like to use the opportunity to write a templated stack, a stack that where I can add whatever elements I want. And then I want to talk more about linked lists, especially raw linked lists. Not a linked list hiding inside of a stack class, but working directly with nodes of lists. Not so much for data structure reasons, but as a way of developing some dexterity with lists and dexterity with recursion, which I feel is something that is intimately tied to the way that lists work.